Hello everyone. Today I'll be talking about the dimension of a vector space. So last time we talked about vector spaces and we talked about the basis of a vector space. And today we're going to show that if you have two bases for a vector space, then they have to contain the same amount of elements. And so that size, the number of elements of your basis is called the dimension of V. So first we're going to prove sort of a technical theorem, and I'm not actually going to go through all of the proof because it gets a little messy, but I will indicate how to do it. So let V1 through Vm be a basis of V, and let W1 through Wn be also elements of V, where n is greater than m. So I have some elements in my vector space, and I have more of them than are in my basis. And so the claim is that then the w sub I are linearly dependent. Okay, so if you have some elements that exceed however many things you have in your basis, then they have to be linearly dependent. Okay. Okay, so let's look at the proof. So assume, to the contrary, that the w sub I are linearly independent. Okay, so let's start with w1. So w1 is not equal to 0. Why? Well, none of the vectors can be 0, because if you have a set that are linearly independent, you can't have 0 in there, because you can think of, like, you can make a linear combination with the coefficient of the 0 vector being non-zero, and then all the rest are 0, and then you would end up with 0. So you can't have 0 in a set of linearly independent vectors. Okay, so now let w1, we're going to express it in terms of the coordinates for the basis, right? Xi, Vi. And since w1 is non-zero, some coordinate x sub I is not 0. Now we can essentially, fancy word here would be permute, or rather relabel the basis so that x1 is not 0. What do I mean by this? This is just like a technical thing. I just mean that it's just for convenience of writing what I'm about to write. And what I mean is that it doesn't really matter which basis vector. It doesn't matter the order your basis vector's in. So if x sub I is the non-zero one, I can just take v sub I and swap it with v1, and then, that works, right? So it becomes x sub I becomes x1, and that's non-zero. Okay. So with x1 equaling 0, okay, then we can solve for v1. Okay, so v1 is going to be 1 over x1 w1 minus, and then we have essentially the rest of the v terms. So we have, x2 over x1 v2 plus blah, 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 all the way up to xm over x1 vm. And notice that this is an element of the span of the vectors w1, v2, up to vm. Okay? So if these vectors span some these vectors span some subspace of V, And that subspace also contains this missing, sort of missing vector, this missing basis vector. So that means the basis of for V is contained in the span, which means the span is actually equal to B. Thus, W1, V2, Vm span all of V, since the basis V1 through Vm is contained in the span. Okay? And so now this is kind of the part in the proof where it gets like really just like messy. And what you do is you use induction to show, essentially, you keep repeating this argument and you keep replacing sort of V2 by W2 and so on. So you show that W1 through Wm, you just keep replacing the basis vectors and you show that these span V. But then, so that's the messy part. That's not the part that, or that's the part that I'm gonna skip. It's essentially the same. You just have to. It's a lot of like indices and stuff that I'm not gonna go through. Okay, but then, since m was less than n, let's take w sub n plus 1, for example. This must be in the span of w1 through wm, implying that and again, w sub m plus 1 is not 0, so this gives us, or I should have, I wrote this the wrong way. So implying that this set is linearly dependent, right? Because if w sub n plus 1 is in the span, then I can write w sub n plus 1 as a non-zero linear combination. And so that means that if I just move w sub n plus 1 to the other side, that gives me a non-zero combination of w1 through wm plus 1, which is equal to 0. And so that means that they're linearly dependent. And this is a contradiction. And what is it contradicting? It's contradicting the assumption that the w sub I, w1 through wn, was linearly independent. Contradiction. Contradiction to w1 through wn being linearly independent. Okay. So this is sort of like a really technical theorem. So let's see what this allows us to prove. So I'm going to state a corollary. So let v1 through vm and w1 through wn be bases for v, then the claim is that m is equal to n, right? So if I have two bases for v, then they have to contain the same number of elements. And the proof is really simple. Essentially applying the theorem with either basis gives m is less than or equal to n, and n is less than or equal to m, so m equals n. Okay. So what I mean by this is that in one direction, right? So if I use this as my basis, the v sub i's, then I go to this theorem and I say, okay, these v sub i's are my basis, and I have some w1 through wn. If n is greater than m, then the wi are linearly dependent. But w1 through wn is a basis, so by definition of a basis, it has to be linearly independent, which means n can't be greater than m. Okay? So that would give me this one, right? And then I would do it the other direction. I would say, okay, I go to this theorem. I would have to sort of relabel everything. But I say, okay, I take this as my basis, and then I have some elements in my vector space. If m were greater than n, then these would be linearly independent, but they're not by definition of a basis. The basis has to be linearly independent. Or I might have said, if m is greater than n, these are linearly dependent, but they're not, right? So that shows that m can't be greater than n. So m is less than or equal to n. Okay? So really this theorem is the technical result, and this corollary is what we want to say, is that if we have two bases for v, they have the same number of elements. And so this allows us to define the number of elements in a basis for v is the dimension of v. So there's something I kind of have neglected to mention, which is sort of the existence of a basis. And sort of we've been dealing with finite bases. So for our intents and purposes, we're only going to be considering finite dimensional vector spaces, in which I believe you can always find a basis. Now, in general, if you have infinite dimensional vector spaces, which often come up in like sort of higher dimensional analysis or quantum mechanics even, then you have to accept what is called the axiom of choice in order to say that any vector space has a basis, even in infinite dimensions. So the axiom of choice is not really controversial, but there's some mathematicians who don't use it just because of some of its implications. But it's all really like a philosophical thing. So usually we'll be explicitly constructing a basis. So I don't want to get into sort of the whole theory of like the general existence of a basis. Okay. Okay. So now we're just gonna prove some more results using the dimension. Okay. So first is just another straight up corollary. Um, so let uh, let V be an n-dimensional vector space. So I'm just going to write that as dim V equals n. And let W be a subspace which contains n linearly independent vectors. Okay. Then the claim is that W is equal to all of V. Okay. So if I have a subspace and I find some n linearly independent vectors in that subspace has to be equal to all of n. So let's see why this is the case. Well, for so let W1 through Wn and W be linearly independent. For any v in V, the set consisting of W1 through Wn and V is linearly dependent by the theorem. So why is that? Well, this set has more than n elements, and so the theorem here is, we can now rephrase it using the dimension, okay? It's saying that if I have some number of elements, and the number exceeds the dimension, then those elements are linearly dependent. So since n is the dimension and I have n plus 1 elements, they have to be linearly dependent. So we have, say, AV plus, and then I'll just write as a linear combination, B sub I, W sub I equal to 0, with some non-zero term, or non-zero coefficient. Okay. So if, let's see what would happen. If A equals 0, then the sum of the W sub I being 0, since they are linearly independent, implies that each B sub I is 0. But that contradicts there being some non-zero coefficient. So this is a contradiction. Thus, A is non-zero, and now what we can do is solve for V. So V is the linear combination negative B sub I over A times W sub I, and this is in the span of W1 through Wn. Okay. Now the span of W1 through Wn, since these are elements of W, this should surely be a subspace of W. Okay. But V is any element of little v is any element of our vector space V, so V is contained in W, but W is contained in V since it's a subspace, implying W equals V. Okay, so this is kind of a neat result. Okay, so the last thing to do is prove sort of a weak version of what's sometimes called the rank nullity theorem. So let F be linear, a linear map from V to W where the dimension of V equals the dimension of W, and we're assuming these to be a finite dimension. Then if the kernel of F is 0, or the image of F is W, then F is an isomorphism. So I didn't prove this in the video about modules, but the kernel of F being 0 is the same thing as F being injective. And this is true like for group homomorphisms, and I'm pretty sure ring homomorphisms as well, if I'm not mistaken. So essentially this is saying that if F is injective or if F is surjective, right, the image being W is clearly just saying that F is surjective. So this is injective or it's surjective, then F is an isomorphism. But remember, for a linear map to be an isomorphism, it just has to be bijective. So this is saying that if F is injective, then it's, or surjective, then it's the other one as well, which is a pretty interesting result. So let's see why this is true. So we're just going to show we're gonna first do this one and then this one, right? So if the kernel of f is 0, f is injective, so we only have to show that f is surjective. Let v1 through vn be a basis for v, then let me see. Let's consider a linear combination of the f of v sub I. Okay? Well, by definition of a linear map, right, a linear combination of f values is just going to be f of the linear combination. And so this is saying that the input here is giving us 0, so that means that the sum of xi vi is in kernel of f. But this is just 0, so each xi is equal to 0, and so the f of v sub I are linearly independent. Okay, so I kind of skipped a little step, so let me elaborate. So here we have that 0 equals a linear combination of the basis vectors, so that means that each coordinate is 0. And so what we've shown is that if we have a linear combination of the f of v sub I, which gives us 0, then that linear combination has to be sort of the 0 combination, right? All the coefficients are 0. Therefore, since n is the dimension of v, but dimension of v equals dimension of w, so I have n linearly independent values in w, which means this is a basis for w. So for any w and w, okay, I can write w in terms of the f of v sub I, and then I can, since this is linear, I can turn this into f of the combination of xi vi, which is in the image of f by definition, right? It's f of some vector. So thus thus f is surjective. So we have f is injective and surjective, therefore it's bijective, and therefore it's an isomorphism. Okay. Now we have to go in the other direction. So if image of f equals w, then f is surjective. Okay, so I'm just going to abbreviate this here. Now we're going to sort of do the opposite of this proof. So we want to show that the kernel is 0. So, and instead of considering a basis for v, we're going to consider a basis for w. So this is a basis for w. Okay. So let v sub I and v be such that f of v sub I is w sub I. Okay. So these v sub I might not be unique a priori, right? But what I'm using here is I'm using the fact that f is surjective. So for each w sub I know that I can write I can write that w value as an image of an element in v. So that's how I'm getting these v sub I values. Okay. So hold on. So now note that if I have a non-zero linear combination of the v sub, or well, if I just have a linear combination of the v sub I giving me 0, then I can apply f on both sides. I get f of the xi vi is equal to f of 0, and any linear map sends 0 to 0 because that's part of, not really part of the definition, but it's part of the consequence that it is a homomorphism at the abelian group level. Okay, remember that a vector space is sort of an abelian group with extra structure. Right? Then so we have 0 is equal to, now since f is linear, I can write this as the linear combination of x sub I, f of v sub I, but f of v sub I is w sub I. And since the w form a basis, if I have 0, this means that each xi is equal to 0. So thus, the v sub I are linearly independent, and therefore, since I have n of them, I have n linearly independent elements in V, which has dimension n, and they form a basis. So if I choose V in the kernel of F, I can write V in terms of the basis. And so 0, which is f of V, I can write as the sum of xi w sub I, which implies that the xi are 0, which implies that V is 0. Okay? So I went a little fast there, so let me back up and explain. So V is in the kernel, okay, and I can write it in terms of these coordinates. So by definition, if V is in the kernel, f of V equals 0. Now I can use the fact that f is linear to write this as a linear combination of f of v sub I, but f of v sub I is w sub I, so I get a linear combination of the w's. The w's are linearly independent, so that means each x sub I equals 0, and if each x sub I is 0, that means that v itself is 0. Okay? So the kernel of f is 0, so f is injective, and that shows, again, f is an isomorphism. Okay? So that concludes video, and in the next few lectures, we'll get to field theory and eventually build up to Galois theory. So I hope to see you then.